So far, we've focused on convergence tests for series that only have positive terms. But what if that's not the case and a series has some positive terms and some negative terms? How can we test for convergence in that case? Today, we're going to look at a few different tests for this sort of scenario. The easiest idea is to compare a series with mixed terms to one where you just take all the positive terms instead. And so we'll look at a couple definitions to start. A series, A sub n, is said to converge absolutely if you take the absolute value of all the terms and it still converges. On the other hand, it's said to converge conditionally if the sum converges, but when you take the absolute values, it no longer does. It turns out that these are the only two ways that a sum can converge. Or in other words, we have this theorem right here that says, if you take the absolute value and your sum converges, then the original sum does as well. In terms of the definitions that we just talked about, that means that absolute convergence implies regular convergence. So let's look at an example and see what that means. In this case, we have the sum from n equals 1 to infinity of minus 1 to the n over n times log n to the 1.1. And so this minus 1 to the n, of course, is making it alternate between plus and minus terms. And so that would mean that we're not allowed to use things like the direct comparison test or the limit comparison test or the integral test as written because this does not have only positive terms. But one option is to compare this to the sum when we only do have positive terms. And so in other words, I'm going to take the absolute value, and if I take the absolute value of what's written up here, then it just drops the minus 1 to the n, because that was the only thing that was negative anyway. And so now I have to figure out whether or not this sum converges or diverges. It turns out that this is one of those cases where it is easy to integrate if I switch to x's instead of n's, because there's a chain rule situation going on. And so if we look at the integral of 1 over x ln x to the 1.1, and so here we do have to note that this is a positive, continuous, decreasing function. And that's why we're allowed to use the integral test. Then I can do a u substitution in order to figure this out. And so I could let u be equal to ln x, which is convenient because in this case, du would be 1 over x dx. If I plug that into this integral, then it's going to end up simplifying to du over u to the 1.1. All right, and we know that this is a convergent integral by the p-test for integrals. And that's just because 1.1 is equal to p here, and that's greater than 1. Okay, so now we know that our original sum, the minus 1 to the n over n times log n to the 1.1, converges absolutely. And that's by the integral test. And so that means that even if we have this minus 1 to the n term here, that doesn't affect whether or not it converges, because even if we just take the plus part of it, it still converges.